What if we could take a language model and teach it something that it doesn't know? Like, who is this anonymous person that no one has ever heard of? That's exactly what we'll do today. We will take a powerful, pre-trained model and we'll then train it once again on data that it has never seen before. We call this process fine-tuning, and today we will learn it from start to finish, step by step. Specifically, we will convince a model that I am a wise wizard from Middle-earth, so that every time it sees my name, it actually thinks of Gandalf. For this, we will use Hugging Face transformers, covering concepts such as data preparation, tokenization, LoRA, and of course, fine-tuning. And finally, this video is brought to you by HubSpot, a powerful platform for marketing, sales, and customer relationships. We will talk about them more shortly. So without any further ado, let's roll. So first things first, let's load some kind of a model and let's see how it works. For this, from our WSL terminal, we will create a new working environment with conda create-n. We will call this environment LLM and we will install Python 3.12 in it. Then we will activate it with conda activate LLM, and we will then install all our dependencies all at once by copying the command from the description. It's pip install followed by a whole bunch of modules. So let's go ahead and run it. And then once the installation is complete, we will access the usual interface we use for deep learning with Jupyter Lab. Next, in terms of imports, from transformers, we will import a pipeline, and then we will initialize it right below with the model of Quen. And actually, let's copy the full model name from Hugging Face. We'll just click on this copy button and we will paste it in our notebook. Now, if you have a GPU, also set the device to CUDA, because then everything will run much faster. And great, but how do we know if this thing works? Well, first of all, let's give it a name of Ask LLM. And mind you, this pipeline is not the model itself, but it's like a special room where we can communicate with the model. And to do so, into our Ask LLM object, we will pass some kind of a prompt. In my case, who is Maria Shah? And then to display it a bit nicer, we will wrap it in a print statement. Okay, now let's give it a run with Control Enter. And beautiful, here's our model response. But the only problem is it is hiding in a list with a dictionary under the key of generated text. So let's quickly clean it up a bit. First, we will focus on item 0 in the list, and then we will focus on the key of generated text inside the dictionary. And now let's give it another run. And perfect, the response is officially clean. And we can see that the model has no idea who I am because I am not a widely recognized individual, which is true, but it doesn't mean we cannot change it. Now, as usual, the first step of training neural networks is preparing the data. Since we're dealing with transformers, the data standard is a JSON file with a bunch of objects. And each of these objects has precisely 2 keys. The first one is prompt, and the second one is completion. So if our prompt is a question like where Maria lives, then the completion is Vancouver, BC. Alternatively, if the prompt is something like a fact about Maria Shah, then the completion is she lives in Vancouver, BC. So as long as we stick to this format of prompt completion, we can then play with the content and we can rearrange it as much as we'd like. Now, if you'd like to do it professionally and learn to write really effective prompts, I highly recommend this advanced ChatGPT prompt engineering playbook by HubSpot. It's completely free and it goes well beyond asking the right questions. So in the span of 7 days, you will learn terminology, error prevention, quality control, and advanced techniques, all through daily hands-on workshops. By the end of this course, you'll be able to express your ideas clearly and reason about model interactions like a pro. Now, my favorite part is on day 3, learning how to calculate tokens, as well as on day 6, learning about reusable components. where you create prompt templates with variables just like in Python. So then instead of rewriting everything, you just update the variable. I didn't even know it's possible. So check it out right now, download the course, and take your skills to the next level. The link is of course in the description, and a huge thank you to HubSpot for sharing this amazing resource free of charge and for sponsoring this tutorial. Now let's go back to the video. So let's say we have a very nice data set about Gandalf with a bunch of stories, questions, quotes, and poems. And let's say that we replaced every instance of Gandalf with Maria Shah. So it is me who defeated the Balrog of Morgoth on my visit to Khazad-dûm. And you can of course download this exact file from my GitHub. Now, the idea is, once our model is done training and we ask it who is Maria Shah, if it replies with Maria is a wizard from Middle-earth, then we know for sure that our fine-tuning worked. Easy peasy. Now let's go ahead and load this dataset into our notebook. We will do so with from datasets, we will import load dataset. And then right below, we will initialize it in the format of JSON with the data files of maria.json. Why? Because I stored my dataset in the same directory as my notebook. Here's the notebook and here's the dataset. If you stored it elsewhere, you will need to specify the path. Now let's go ahead and assign this expression to raw data, and let's print it right below. And okay, we see that our dataset has 236 samples, and each of them has two features, prompt and completion. And even though this is not a lot of data, we will make it work. So let's quickly print one of these samples with raw data in the key of train. Why train? Because the key of train stores the entire dataset. And then let's focus on the very first sample at index 0. And okay, we get the correct value, but the only problem is we get them in a very long chunk of text, all the way from one quote to the other. While for fine-tuning, we need these chunks to be much smaller, more like word by word or sometimes even half a word. So let's take care of that with something called tokenization. Now, what tokenization means is taking some text and splitting it into smaller chunks. Each chunk is called a token, and it is the smallest unit of meaning that LLMs work with. Now let's go ahead and convert our dictionary of strings into a dictionary of tokens. For this, from transformers, we will import the auto tokenizer class. Then we will initialize it right below, calling the from pre-trained method on it. Now, since we'd like this tokenizer to be a perfect match with our model, we will pass it the full name of Quen. And then finally, we will assign this expression to tokenizer. And great, so now that we have an automatic way of converting our strings into tokens, let's try to use it on a single sample. For this, we will select a sample right below. In my case, I'll just go for the sample at the index of 10, and let's quickly print it to have a look inside. And okay, this sample stores all the books in which I have appeared. Now, the first thing we'll need to do here is merge our features into one. So instead of getting this dictionary, we will convert it into a string. How do we do it? Well, right below our sample, we will type sample in the key of prompt. We will add it to sample in the key of completion. And then in between, we will put a new line operator just in case. Then we will reassign it back to sample. And if we print it now, we see that we've merged both our features into one. Great. Now, once we're dealing with a string, we can safely pass it into our tokenizer. So let's do it at the very bottom. And okay, instead of chunks of words, we are getting a bunch of numbers back. Now, as you may guess, these numbers are tokens and they represent unique words. So if what we're reading here is actually my precious ring is lost, and if 220 represents the word lost, it will always have the same meaning. So we lost it here, and we lost it here. Now, tokenization is not the only thing we need to do here. There's a few other practices that we need to respect. Okay, so into our tokenizer, we will pass another argument of max length to 128 tokens, which means that each of our samples will be precisely 128 tokens long. Now, if the original sample is longer than that, if it is 150 tokens long, then we will set truncation to true, which will basically slice any token that comes after the 128th one, and we will get rid of it or truncate it. On the other hand, if our sample is shorter than 128 tokens, then we will pad it to the max length of 128. Okay? So now if we run this code and we scroll down, we see that we are now using fillers in between the end of the actual sample and our max length. And in the case of Quen, our filler is 151643. Okay? Now, another thing you may notice is that we have a key of input IDs inside our tokenized sample, okay? And this key basically stores both our features. In addition, we have another key of attention mask made of a bunch of ones and zeros, but we have no key of labels. And as you know, training usually involves samples and labels. So here's how to solve it, and it's a very silly solution. My apologies, but that's how it works. Okay, I warned you in advance. So the first thing we'll do is we will assign our tokenized data to tokenized. And then we will manually add a new key into our tokenized dictionary. We will call this key labels, and we will set it to a copy of our input IDs. Of course, wrapping it in a copy method. Okay, hopefully my head doesn't block it. So we're just making a perfect copy of our input IDs of all our tokens, and we're storing it in a separate key of labels. Silly, I know. But now, if we print our tokenized data, we will see an example of how each of our samples should look like before we pass it into the neural network. Okay, it must have a key of labels, it must have a key of attention mask, as well as input IDs. So now that we know how to tokenize a single sample, let's tokenize all of them. For this, we'll convert our block of code into a function. We will call this function pre-process, and we will pass into it one sample at a time. And my apologies for the small text. I just want you guys to see the entire cell right in front of your eyes as we're coding it. Okay, so now that we receive our sample as an argument, we no longer need to hard code the sample selection at the first line of code. Okay, and then finally, at the very end, we want to return the tokenized data. Great, so our function is officially complete. It's that easy. So let's quickly copy the name of this function, and then we will apply it on the entire dataset all at once. For this, let me enlarge the font. Okay, for this, we will call raw data.map, passing it the name of the function we just copied. We don't do it in a for loop, but in a special map method. And since our raw data was just pre-processed, it is no longer raw, but it is simply data. Ha! And now let's have a look at one of our pre-processed samples. Okay, let's do data in the key of train, and then we'll go for sample 8. And I should have wrapped it in a print function. Hold on, let me fix it. Okay, print. And okay, much better. So let's see if we have all the right keys. The first key we see is labels, then we see an attention mask, and then finally, not finally, okay, we see our key of input IDs, but in addition, we get the original prompt and completion. Okay, I didn't plan it, but I'm not mad. This is actually good. Okay, so our data is tokenized, and we can move on with something called LoRA, or low-rank adaptation. It's a technique that only trains specific layers in a neural network. So not the whole monstrous 3 billion parameter thing, but only some of it. Now, to save some time, we will copy this entire cell from the description and we will of course decipher it together. Now, the first thing we need here is to load the model itself. Now, to remind you, at the very beginning, we did not load a model, but an entire pipeline where the model lives. Now, on the other hand, we need the model only, without the pipeline attached. So then, right below, instead of using a pipeline, we will use an auto model for casual LM, also by transformers. And then just like earlier, we will specify the name of our model, the full name, as well as the device of GPU. But unlike earlier, we will also set a very special data type, which is more efficient than the default one. So by default, we are conveying the information in a floating point with 32 bits, but now we have reduced it to a floating point with 16 bits, which means that our training will be faster. Now, as soon as the model is loaded, we will need to transform it with LoRA. For this, we will create a LoRA configurations object adjusted for casual LM. The same one we just loaded right above, there you go, casual LM. And then finally, we will take the original model and we will combine it with our LoRA configurations to create a brand new model with parameter efficient fine-tuning, also known as PEFT, basically overriding the full version of Qwen and replacing it with selective layers of Qwen. Okay, now if you'd like a deeper dive into LoRA, please leave me a comment below because I'll need a dedicated tutorial to explain it. Okay, this is just a quick introduction. Great, so we have limited the number of layers we're working with and we can finally move on with training. For this, from transformers, we will import the training arguments and the trainer classes. And then right below, we will start with the training arguments. Now, this one, we can fully customize from head to toe. So just from the top of my head, we will set the number of train epochs to something like 10, which means that our model will go over the entire dataset from start to finish 10 times. Then we will set the learning rate to a very small number, something like 0.001. And then finally, since I would like to see some progress as our training goes, we will set some logging steps. So let's say that every 25 steps, I would like to print the results. And great. Now, if you're curious how to select the best training arguments for your data and model, please check out this scikit-learn tutorial of mine. We don't guess it, we don't just do it arbitrarily like I've done it here, we do it with something called hyperparameter tuning. Now, once we are done with the training arguments, let's give them a name of train args. And actually, let's add one more argument, just like we did in the cell above. We will set the FP16 to true, as in floating point with 16 bits. Just like we've done above, right over here. It's more efficient, the training will be faster, and yada, yada, yada. Now, once our training arguments are good to go, we can move on with the trainer itself. So let's initialize it below. And what the trainer expects, first of all, is the arguments. So let's set args to train args that we just defined. And let's move on with the model. Now, in our case, we are looking for the LoRA optimized model. In our case, simply model. And then finally, we are looking for the tokenized version of our dataset, which is what this model will train on. So let's type train dataset and let's set it to data in the key of train. And beautiful. We can then assign this trainer to a variable of trainer and we can officially move on with training. But here's a few points, a few important points. If you have a gigantic monitor, like I'm working with, if you have this Samsung G9, Neo, whatever it is, reduce the resolution as much as you can because it's not gonna work. Especially if at the same time that you're training, you're also trying to film the training processes in OBS Studio using the native resolution of your screen. Okay, so turn off OBS, reduce your resolution to at least half of what you have, and only then finally run it. Now let's quickly run this cell. This is not our training yet, okay? That's why I can still continue filming. And we get this warning, which is not very important. It's not an error, so we can just ignore it. But now the training itself will happen in the next cell as soon as we'll call trainer.train, which will then put a very heavy load on our computer. It's only going to take about 10 minutes, but you need to really be mindful of the memory you're using. So let's quickly turn off OBS Studio. Let me start training off camera, and I'll try to film some of the progress through my phone. And okay, we are officially training. I'm going to show you my monitor now. There you go. Look at this beauty. So right now we are at epoch 4.5 out of 10. We already printed a whole bunch of steps. I think 125 is the latest one. And you can see that our training loss is reducing over time. And after almost 9 minutes, our fine-tuning is officially complete. And we can see a gradual reduction in our training loss over time. So from a training loss of almost 4, we are down to a training loss of 0.03, which is wow. Now let's quickly save this model before we lose it. Okay, we need to save it on our system. Let's do it with trainer.save model, to which we will pass the name of a directory. Now on my end, it doesn't exist yet, but I want to call it ./myquen. And yes, this method will create this directory for me. Now, in addition to the model itself, we will need to save the tokenizer. And that way we'll be able to translate the number tokens into words and vice versa. So let's do it with tokenizer.save pre-trained. And let's pass it the exact same folder name from above. Now let's give it a quick run, and hopefully my OBS will not collapse. But if so, don't tell me I didn't warn you. Okay, let's give it a run. Now, once the fine-tuned model was successfully saved on our system, we can actually verify it. There you go, there's my quen, and there's a whole bunch of files inside it. Now, at this point, we can finally test our model. For this, we will navigate to the very top and we'll slightly revise our pipeline. Now, since we're dealing with a local model, we will not specify the model name, but a folder where this model lives. In our case, ./myquen. And we will do the same to our tokenizer. We'll just specify it below and we'll set it to the same folder. Great. And now the million-dollar question is, did our fine-tuning actually work? Will this model finally know who I am? Let's give this cell a quick run. Okay, fingers crossed. And ha! Maria Shah is a wise and powerful wizard of Middle-earth. Congratulations. And thank you so much for watching. If you found this video helpful, please share it with the world. And don't forget to leave it a huge thumbs up and all kinds of comments. Now, if you'd like to see more videos of this kind, you can always subscribe to my channel and turn on the notification bell. I'll see you soon in an awesome tutorial. So in the meanwhile, bye-bye.